Hello, everybody. Sorry I can't be there today, but here we are, ready to do section 4.4, which is all about the fundamental theorem of calculus. So before we start with what that theorem is, we are going to discuss the difference between an indefinite integral and a definite integral, which are two things that we've been talking about in our class. So both of these involve doing an antiderivative. So an integral is an antiderivative. So for the indefinite integral, let's write, oh boy, let me lock the screen. Okay, so let me write antiderivative. And your answer is a function. So when you perform an indefinite integral, you are going to end up with a function rather than a number as your answer. When you do a definite integral, you are still taking an antiderivative, but you are evaluating it at your upper and your lower bounds, which you haven't done yet, but that's what we're going to do today. So it's an antiderivative evaluated at the bounds. Your answer will be a number rather than a function. And what it represents is the area under the curve. Between x equals a and x equals b. So the answer is a number rather than a function, and that number is giving you the area under the curve, which we have talked about in this class already. So let's talk about how we're going to do these algebraically. So that's the fundamental theorem of calculus here. I will highlight it because it's fundamental. If a function little f is continuous on the closed interval a to b, and capital F is an antiderivative of little f on the interval a to b, then this is true. So basically what this is saying is that if we've got our integral with our lower and upper bounds here and here, we can take the antiderivative, which is this capital F. So the capital F is the antiderivative of the little f. And we would evaluate it at B and at A, and we would subtract those. So we have the image there to show that it's the area under the curve of little f between A and B, and that we have already talked about several times. The notation for when we do one of these antiderivatives is the following. So we would do integral from A to B of little f is equal to capital F, and we usually write evaluated from A to B, and then that is capital F of B minus capital F of A, which we will practice with in just a moment. So at first this might feel a little confusing, but it'll make sense. And we use this all the time. It's literally the fundamental theorem of calculus, so it comes up a lot, and we want to get very, very comfortable with it. Okay, so here we have an example. Evaluate the definite integral of that function there from 2 to 6. So we're going to start off, let's just write it down. we start off by just getting the antiderivative of the function. So that's where we use our integration rules, where we increase the exponent by 1 and then divide by that number. So here we're going to get, okay, 3x squared will become x cubed. X will be x squared over 2. 2 will be 2x. And I'm going to write plus c. Okay, so if there were no bounds on the integral, we would be done. If it was an indefinite integral, we would be done. But it's a definite integral. And so what we're going to need to do is we're going to need to evaluate this at those bounds, the upper and lower bounds. And this is usually the notation you'll see for that. So I'll highlight my lower and my upper. All right, now that means we're going to do the upper bound first. So let me go and get yellow. Okay, so this is going to be equal to, now I'm going to plug in, and we're going to be very careful using brackets. I'm going to plug in 6 to my function. And then I am going to subtract whatever I get when I plug in 2 to my function. So we do plug in the upper bound minus plug in the lower bound. And that's coming from, again, this fundamental theorem of calculus up here, f of b minus f of a. Okay, so then we're going to do 2 cubed plus 2 squared over 2 minus 2 times 2 plus c. Okay, and then you would evaluate each of those. Definitely feel free to use a calculator if you're just doing this on your homework. That's fine. So on this one, I believe, you can double check, I think we're going to get 222 plus c. And for that second one, we get 6 plus c, which would be 222 plus c minus 6. I'm just distributing this negative, minus c. And so you can see that the c's go away. And I want you to think about, will that always happen? Pause the video. Did you pause it? Did you think about it? Okay. Yes, that will always happen because you're always going to have a plus c in your first one and a plus c in your second one, and you're always going to be subtracting them. And so therefore the constants cancel out. So whenever you do a definite integral, you actually don't need to worry about writing the plus c if you don't want to. Like, most people don't write it down. If you feel like not writing it is going to make you forget to do it on the indefinite integrals, then maybe you should keep writing it. But you're going to see me not write down the c when I'm evaluating a definite integral. Okay, so my final answer here would be 216. So see how we're getting a number as our answer rather than a function. And that number would represent the area of the region between the function 3x squared plus x minus 2, the x-axis, and then the vertical lines x equals 2 and x equals 6. Okay. Oh, and you can always check your answer for these definite integrals on your calculator. Remember, you hit the math button, and I believe it's option 9. So the calculator can evaluate a definite integral for you. Okay, so we might not do all of these ones, but we'll at least get them started, just for the sake of keeping the video shorter. So let's do the first one for sure. This you would like to maybe rewrite it as the definite integral from 4 to 9 of 3, and then I'm just going to put that's x to the 1/2, just as a reminder. Okay, so we're going to start off by just doing the integral of 3x to the 1/2. I increase my exponent by 1, it will become 3/2, and then I divide by 3/2. And if you remember last class, we talked about the dividing by 3/2 is the same as multiplying by 2/3. So I'll write it out anyway. Let's see. So we're going to get 3x to the 3/2 divided by 3/2 evaluated from 4 to 9. So I'm not putting down the plus c because I know that it's going to just go away. Okay, and then this is equivalent to, okay, I'm going to show my work not in the best way. This is like multiplying by 2/3. Also, that 3 in the denominator is going to cancel out with that 3. So really, I'm left with 2x to the 3/2 evaluated from 4 to 9. Okay, we're going to plug in the 9 first. So I'm going to have 2 times 9 to the 3/2 minus 2 times 4 to the 3/2. Okay, to the 3/2, that means we're going to do the square root. Square root of 9 is 3. 3 cubed is 27. 27 times 2 is 54. Square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. And that is 38. Okay, that's what we're getting there. Okay, option B, I'm gonna leave that one for you guys to try if you just want to practice it. Your answer should end up being 0, okay? And by the way, this down here should say, why was the answer to part B 0 down here? Right now it says part C, it should say part B. So after you do that one, get 0, I want you to think about it geometrically. So sketch a little graph of that line and think about why are we getting 0? Does it make sense geometrically? Okay, for part C, antiderivative of secant squared. If you remember some of your derivative rules, you can think about it that way. Or if you want to look at your bright blue sheet for now, antiderivative of secant squared, see if you can find a formula for that. You're going to get that it is tangent. So this is going to be tangent of x evaluated from 0 to pi over 4. And then you would just plug in, you would do tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1. Tangent of 0 is 0. We get 1 as our final answer. Okay, and then D is kind of a funky one, so we're not going to do it all the way through, but we'll do the more challenging part together. So how the heck would we integrate an absolute value function? So it's been a little while since we've talked about this, but hopefully you remember that we did discuss that we can always write an absolute value function as a piecewise function. So you can rewrite an absolute value function as a piecewise function. In order to do that, you do want to first think about where the pointy piece happens. So, right, we know that the absolute value graph looks like that. We want to think about where the little point happens. So for this one, or for all of them, it's going to happen when the function is equal to 0, because it's actually not for all of them. I lied. So long as the function is not being shifted up or down, we're going to think about where it equals 0. So this doesn't have any vertical transformations. It only has horizontal shifts. Anyway, I'm getting a little. When in doubt, just graph it. Graph it on your calculator if you're not sure what the heck I'm talking about. Okay, so I'm going to set the function equal to 0, and I'm going to get x is 1/2, which tells me that this little pointy piece is happening at the x value 1/2. Okay, so if this is like 0, that piece is happening at 1/2. And so that's where I'm going to split up. When I write my absolute value function, I'm going to have one thing if x is less than 1/2, and I'm going to have another if x is greater than 1/2. Okay, the first one when x is less than 1/2 is I can see my line is sloping down, so that's going to be negative 2x minus 1. And then this one will just be 2x minus 1. Okay. So, if you do graph it, here, I'll do a little sketch. Where can I fit it? Okay, let's just do it right here. This isn't going to be perfect, but 1/2 is where it's going to like cut my absolute value function in half. This half is going to be the line. That is the line negative 2x minus 1, which you see is negative 2x plus 1. So it's a line with a y-intercept of 1 and a slope of negative 2. And then the other half of it is like over here. Oops, that's a different color. And that line is 2x minus 1. So if we continued it, it would have a y-intercept of negative 1, and it has a slope of positive 2. So now all we're doing is we're kind of breaking this up into two integrals. So we're going to break it up. We're going to say that when we integrate this from 0 to 2, instead of doing that, we're going to integrate the top half from 0 to 1/2. So let's do that. So we're going to rewrite our integral as from 0 to 1/2 of negative 2x minus 1, which I would just distribute it. So if you feel comfortable, just go straight to negative 2x plus 1 dx plus, so that's coming from our first half. And then we've got our second half, which is going to be this one. So now we will add our integral from 1/2 until 2 of 2x minus 1. Okay, graphically, we can see that that would be the area over here, assuming that this is 2. Okay, this is 1/2. And then that one is right there. And if you add those together, you've got the area under the whole curve. So that's just a little kind of like a trick when you're dealing with an absolute value function. You can get rid of it by writing it as a piecewise function and then integrating into pieces. And I think you guys can handle it from there. The computation gets like a little bit annoying, but this is also a really nice one to just do graphically or geometrically because you've got two triangles, so you could add them together. So I recommend that you work this out, right? You're going to do this one and this one, see what you get, add them together. And I believe your answer should end up being 2.5. You don't have to do it right now. You can try it later. Okay, and then this last page, these are AP style questions. AP style questions, just so you can see. how they like to get a little creative. So for this first one, we're being given a table that gives us quite a bit of information about a function, its first derivative, and its second derivative. And we're being asked to find the value of f prime, the integral of f prime of x evaluated from -3 to 1. Okay, so we know that we don't actually know what the function is, so we can't find, we can't actually perform the antiderivative, but you should know that the antiderivative is going to go backwards. So if we are integrating f prime of x, the function we would end up with is f of x evaluated from -3 to 1, which is just f of 1 minus f of -3. Okay, so you're going to end up seeing this a lot, and you want to get comfortable going straight from this step. I mean, it's not mandatory to this step. It's not mandatory to get comfortable with that. It's just, I don't know, just you're going to see it a lot. So going straight from step 1 to that third step there. And then you would use your table to find those values. So f of 1 is -2. F of -3 is 4. And so we're getting -6 for our answer. Okay, you can do a similar process for the second one, but now you've got it in two pieces. So, I mean, you could think of it all together or separately. Maybe it's helpful for now if we break it up. So you can think about this as this plus this. Okay, so for the first one, we just did that except with different upper and lower bounds. We're integrating f prime. That means we're going back to the function f. So this one's going to be f of 3 minus f of -1. So that's the first one. And then for the second one, plus, we're going to end up with whatever we get over here. So we're going backwards from f double prime. So the antiderivative of the second derivative would be the first derivative. And so we would have the first derivative evaluated at 3 minus the first derivative evaluated at -1. And then you would find each of those and see what you get. Okay, so let's see. F of 3 is 1. F of -1 is 0. F prime of 3 is 3. F prime of -1 is 1. Okay, so we're getting 1 plus 2, I think. No, yeah. 1 plus 2 is 3. Okay, hopefully you guys got that too. Okay, use the equation of the tangent line at x equals 3 to approximate the value of f of 3.1. Okay, this is review. Use the equation of the tangent line at x equals 3 to approximate the value of f of 3.1. So we don't have 3.1 on our table, and so we are going to use 3 because 3 is closest to 3.1. Okay, so the tangent line is going to be now y minus y1 equals m times x minus x1. Okay, I encourage you guys to pause and think about this one because this is what we learned in 3.7, 3.9. So pause it and then check your work. Okay, so my point is going to be 3, 1. I'm getting that from here. And then my slope is going to be f prime, the derivative function, evaluated at 3. F prime of 3 is 3. So I would have y minus 1 equals 3 times the quantity x minus 3. Add the 1 over. I'm going to write it in the front. And from here, you would plug in your 3.1 for your approximation, and you would be plugging it into x. Oh boy. There go my AirPods. Okay. Hopefully you can still hear me. So you would just plug in 3.1 there and see what you end up with. So we have 1 plus 3 times 3.1 minus 3 is 0.1. So that's 1.3. Great. Okay. Lastly, we've got one using a graph. So the first one is using a table. This one you're being given different information. It's a graph. What is the value of the definite integral f prime from 0 to 6? Okay, so this is what a lot of people end up doing. They end up going, oh, well, it's going to be f of 6 minus f of 0. So that's really good thinking, and that is true. But the information that's given to us is f prime, not f. So this one wants you to find the area under the curve, just like we were doing 1 or 2 lessons ago. So we're going to actually find the area under the curve, which you can do this however you want. You can divvy it up into some different shapes here. I don't know. Lots of different ways you can do it. But you would be finding, oh, guess we don't need that line. Oh boy. You'd be finding the area under the curve from 0 to 6. So this whole region. So I would do maybe like you've got a triangle here. You've got a rectangle here. And you've got a triangle there. Okay, you don't have to do it that way. You can divide it up in other ways too. But that's one idea. Actually, that's, yeah. Okay, and maybe you think of a better way than me. So go ahead and do that. You're going to find that area, and that's going to be your answer. So you can pause, do that. Compare with each other. I'm not going to do it right now. And then for number 2, f of 0 equals -3. What is the value of f of 3? So notice this one, we're being given f prime. We're being given the graph of f prime, and we are being asked questions about f. So this is a classic fundamental theorem of calculus type of a question. And the more you see it, the better you're going to get. But at first, it's kind of like, well, how the heck am I going to do this, right? So again, I'd encourage you to pause and think about it on your own for a moment. But I'm going to continue talking now. So if you're stuck, here's how you do it. You're going to take the values that are given here. So you're given the x values 0 and 3. Okay, we're being asked about f and we're being given f prime. So we need to try to write something out that's going to connect those two. Well, here's what's going to connect those. The integral from 0 to 3 of f prime should be equal to f of 3 minus f of 0. That is the fundamental theorem of calculus that we've been doing. That's what we did up here on number 1. Okay? That's also what's written here in this box. That's the fundamental theorem of calculus. So, this is a connection that we can write. And now we should be able to solve it. So, we know f of 0 is -3. That was given. F of 0 is -3. So, we know that this is -3. So, let's maybe rewrite this. We're trying to find f of 3. So, I'm just going to rewrite. So, this is -3. So, let's rewrite it. F of 3 is going to be equal to, let's add the -3 to the other side. Add the -3 to the other side. So this -3 plus this integral. Great. And now you might be like, well, how do I evaluate the integral? Well, remember, you have your graph right here. So from 0 to 3 is going to be that yellow shaded region. It's the area under the curve right there. So what have we got? We have a triangle with a base of 3, a height of 2. 3 times 2 is 6. Half of that is 3. So I believe this is 0. Yeah? Because we're getting -3 plus 3. Great. Okay. 0. But that's how you do that type of a question. So this is like the AP people love those types of questions. This is very, very common. It's called the fundamental theorem of calculus. So they really make sure to test on it. Okay, so this will be asked in a variety of ways. It's also very popular on FRQs. So you're going to see it a lot more in this class so that we keep practicing with it. But make sure you go back and definitely review that type. All right. I hope the lesson made sense to you, and I look forward to seeing you all on Thursday. Have a great rest of your day, and feel free to let me know if you have any questions.